Okay, so why is it interesting to find statements that don't look the same at all, but are actually logically equivalent, right? Well, so this is what I was referring to when I said proving things indirectly, right? So, uh, if you can't prove this statement, but this other statement looks easier to prove, then you prove the other statement, and then you say, well, these two are logically equivalent. They're if and only if. Therefore, if this is true, then this is true, and if this is false, this is false. Um, so yeah, that's what it is. We're trying to find of new ways of finding proofs. Well, let's catch up and like all the different ways of proving things, right? So, uh, techniques for proofs, let's say. All right. Well, all right. So most of the videos that you've seen from me, if you watch this in order, they were direct proofs, right? So let's just put that in the side, right? So direct proof, Well, so what's a direct proof? Just going from A to B. So starting from the yeah, I guess so, right? Starting from the given, starting from the givens, the assumptions, the hypotheses is what we call it, and ending with the conclusion. Conclusion. I'm just well, so what I mean is that okay, when math people prove stuff, they're usually proving if P then Q statements, right? If P then Q. What we're saying, a direct proof. All I'm saying is that you assume that the statement P is true, and then do a bunch of math manipulation to arrive to show that then it has to mean that Q is also true. That's what I mean from starting from the givens, from the hypotheses, and ending with the conclusion that you wanted, right? Another way to prove things, well, this is more like disproving things, right? Like I said before, in order for you to prove something, you gotta give some type of argument that's convincing, right? And mathematicians are pretty let's expecting. They have high standards for what is a convincing argument. However, I did say this, that in order to disprove something, all you need is a counterexample, and technically disproving a statement is just basically proving that the statement is wrong, right? It's false. So let's just say what's another technique for proving stuff, or more like disproving in this, proving that a statement is false is I guess disprove by example. I don't know what would be the right word to call it. Disprove by example, by counterexample, I should say. Counter example. So yeah, I mean, like I said, there's a lot of. You can probably come up with a bunch of things that you can just think. Oh, I think this is true, and then someone comes to you like, no, I actually have a counterexample to this, right? Okay, so these are the two techniques that we talked about a lot, at least in the prologue series. I mean, okay, as far as if you really want an example of this, it's like if I told you probably don't know what a prime number is. Maybe you do, right? But one thing that you notice about prime numbers is that you might think, oh, they're all odd, right? And then someone might say, oh, then you're a prime if and only if you are odd. Well, if I say if and only if, then that muddles the water, right? Because there's all you need to disprove that statement is to find one odd number that's not prime, Or even if you say, oh, all prime numbers are odd, again, then if you find an odd number that's even, then that disproves it. And then if you do, okay, all prime numbers except 2 are odd, okay, then finally, you made your statement finally true. So anyways, right, so again, there's going to be a lot of examples too, when I mean, again, you can just come up with your own statement, and I'm pretty sure I can find a counterexample, and that will serve as an example to this, right? But let's move on. I don't know, I'm wasting so much time on this. Right, so again, these are the two techniques that we've seen so far. What's let me show you something that's new, right? This is like a crown jewel for mathematicians. I'll just say it like this up. Proof by contradiction. What does that mean, proof by contradiction? So we can talk. I could spend a whole video just talking about this particular one. Here's the gist of what the proof by contradiction is. I'll show you this. I'll just tell you right now. The negation of the statement if P then Q. The negation of the statement if P then Q is equivalent to the following. So this statement is equivalent to this following statement. P and not Q. Alright, so these two statements are equivalent, and basically what a proof by contradiction is, in the simplest way to put it, is that in order to prove an if P then Q statement, you consider the statement P and not Q, right? P and the negation of Q. And what you prove is that every time if you assume P and not Q, you will eventually get a contradiction. Meaning that it turns out that this statement is always false. But if this statement is always false and this is equivalent to this, then this statement is always false. But then if this statement is always false, the negation of if P then Q, then that means that if P then Q itself is always true. So this is what I mean by mathematicians being tricky and being able to prove something without actually proving it directly, but instead of being sneaky about it, right? So let me just do it real quick, right? So let me just show a truth table, because I do, this is such an important thing that I do need, I need to show you that it is true. P then Q, right? So P then Q. So what are we gonna need, right? We need this statement, because once we know that statement, then we're gonna know the negation of if P then Q, right? What else? And then we're trying to find P and not Q, right? So we need not Q, and then we're gonna look at P and not Q. Okay, so how does this go? True, true, false, false, true, false, true, false, and then it also is true, false, true, true. So then this makes this statement be false, true, false, false. Okay, then the not Q becomes false, true, false, true. And then now we're looking at P and not Q. So P is over here and not Q is this one, right? So in the first case, if P is true and Q is false, then P and not Q is false, right? On the second one, this one's true and over here is true. So true and true makes it true. Over here, false and false makes it false. True and false makes it false. So as you can see, what I said before, right? You can already see that these match, right? F this whole thing matches with this whole thing, right? So I'm just saying, I don't really want to bother do one more of like this, if and only if that, because they match, you know. If this is false, that's true. If this is true and this is true, that's true. This is false, that's true, and this is false, that's true, right? So yeah, again, that's math people being sneaky, right? They basically prove that by proving that P and not Q is always false, then they're really proving that the negation of P and Q is always false. But then if the negation of P and Q is always false, then P and Q itself has to be always true. I don't want to do an example of a proof by contradiction right now, because trust me, it's the rest of our lives, or at least it's the rest of this channel. This channel, you will see so many proof by contradictions. It's not gonna be funny. Okay, I don't want to make this a big video, so let's move on to another technique, right? So what's another technique, sneaky way, right, to prove something without actually proving it directly? Well, here's another one, right? Proof by contrapositive. Contrapositive. I think it's supposed to be one word, whatever. So here's the gist of this one. The statement if P then Q is equivalent to the statement not Q then not P. Alright, I don't know, think about it for a while, right? Does that actually make sense? Well, according to the truth tables, it's gonna make sense. But let's see, for example, if the statement is if I splash you with water, then you're gonna get wet. So then the negation for that, well, the contrapositive for that is apparently if you're not wet, then you didn't get splashed by water. Does that make sense? I mean, that's just one example, right? So, just making sure that we're not going crazy and just accepting everything that a truth table tells you, right? Think of more if P then Q statements and see if they do sound equivalent to if not Q then not P. All right, but let me do the two tables. So again, P, Q. So we're gonna need if P then Q. What are we gonna need? And then on this side, we're gonna need the not P, the not Q. You know what? I'm gonna do not Q first, and then not P second. And then we're gonna need not Q, then not P. Right? I think that's all we need. So same old. True, true, false, false. True, false, true, false, right? And then this is going to be true, false, true, true. Okay, not Q, this one's false, true, false, true. And then not P is false, false, true, true, right? So then how do we handle not Q then not P? Well, okay, not Q implies not P, right? So the fact that not Q is false right here automatically makes this true, remember? If this is true but this is false, then this has to be false. Okay, on the other hand, this is false right from the get-go, so then it's just true. And if this is true, then that's true, then that's true. Again, right? I mean, is that a little bit weird that, again, right? They match again, right? These two. Like again, if you have been thinking of your own if P then Q and thinking, is that always really equivalent to not Q implies not P? Well, so again, the truth table seem to agree that yes, they are equivalent, right? But let me know if you came up with an if P then Q statement, and then when you're translating into a not Q then not P, then it no longer makes sense. I'd be very interested to hear something like that. So leave it down in the comments, right? Okay, so proof. So what do we have so far? Direct proof, proof by a counterexample or disprove by counterexample, proof by contradiction, proof by contrapositive. Let's see. Proof by contradiction is going to be a big one, and then proof by contrapositive is going to come in clutch. I sound like such an old man saying that, but yeah, you'll see there are some times where proof by contrapositive just feels like it comes down to you from heaven. That being said, let me specify some things, right? So why do they call it contrapositive? I guess this doesn't really is that important, but so if you have the statement if P then Q, right? P then Q, right? With this in mind, the statement, I don't know if I just call it definition, but the statement if Q then P, the statement if Q then P is the converse of if P then Q. So that already gives you like some vocabulary for a lot of things, right? So for example, if a statement if P then Q and its converse is also true, then you know you have an if and only if statement, right? Let me give you another word definition. The statement not P implies not Q is the inverse of if P then Q. So again, if you have P then Q, then not P implies not Q, basically making them their negations, kind of like making them negative, right? If you have the statement P then Q, then not P implies not Q is the inverse of it. But then if you just flip them, Q implies P, that's a converse, right? So a little fun thing is about this contrapositive is that it just looks like the contrapositive, not Q plus not P. Well, would you say that that's the converse of the inverse of if P then Q? Or would you say that it's the inverse of the converse of if P then Q? Or would you say it's both? The inverse of the converse is the converse of the inverse, right? I don't know. It's fun stuff like that it's probably not fun for everyone, and you're probably thinking, no, that sounds horrible. But I don't know. It's just funny how math people are like that. They create these languages like contrapositive, converse, inverse, and it's funny. It's fun to play around with it. I guess we're supposed to be very serious about math. I suppose like remember what the converse of a statement is. Remember what the inverse of a statement is. But I don't know. I like to have fun. It's funny how it's called the contrapositive, but why is it called the contrapositive? Because it's the converse of the inverse, or because it's the inverse of the converse? I don't know. I'll let you decide. Well, there's again. I want to show you one more thing, right? These are the major ones, really. But I guess one that's very true that a lot of people use to prove things is proof by cases. Suppose there's something that is true, right? But there's like 4 different cases that you gotta try out. So can you say logically that if I prove these 4 cases, then I proved it? I'll show you later what I mean, right? But let me show you this, right? So the statement. So proof by cases, let's say. So the statement if P or Q then R is logically equivalent to the statement P implies R and Q implies R. I use my red color. I mean, so for example, I'm saying this says if P or Q implies R, then it must be if that's true, the only way P or Q implies R is if and only if P implies R and Q implies R. So for example, let's say that you notice something about the natural numbers. You say, oh, I think I know something about natural numbers. I don't know how to do it. And then someone comes in, oh, Well, what if you do two cases? Suppose when the natural numbers are even, and then suppose when the natural numbers are odd. If you've proven that this statement, so think of P as the even natural numbers, and the Q as the odd natural numbers, right? Suppose you say your statement says, if X is a natural number, then something needs to happen, right? Then R happens. If X is a natural number, then R needs to happen, right? But again, you split up the fact that natural numbers can be even or odd into the statement P and Q, right? Well, basically we're saying, okay, well, if you can prove that the statement that statement is true for the even numbers, meaning that the even numbers imply that R statement, right? And if you also prove that the odd numbers also imply that R statement, then yeah, basically even and odd numbers imply that statement. I don't know, hopefully, I think that made sense. So this, yeah, I mean, there are times where you're gonna have to do a proof, like suppose if X is positive, suppose if you prove that something is true for X being positive, if you prove it for X being negative, and if you also prove it for X being 0, those are the only three cases. So whatever it is that you prove, you can also say, I've also proved it for all real numbers. All right. So proof by cases. I'm just saying that these are logical equivalents. So it's okay to split up. It's logically okay to split up something if you have to split it up in cases. Well, let's look at the truth tables, right? Now, notice how we have P, Q, and R. Now we have three letters, right? Man, how am I gonna do this? Well, notice that when we had one letter, it was only two cases, right? When we only had one letter, it was either true or false, right? Now, when we had two letters, we had 4. But why 4? If you didn't really ask why was it 4? Well, notice how, okay, when it's one, it's true false, right? And notice how we have true false right here and then true false again. It's just that in this situation now, this is true and this is false, right? Well, if I'm going to use three letters, P, Q, and R, right? And I'm trying to account for all the possibilities. So P, Q, and R. Hopefully I have enough space. Well, what I'm saying is that I already know that between two things, they're gonna go down like this, right? If I only had one thing, it's either true or false. But if I had two things, basically I consider, okay, when it's true and false, but then this one's true, or when it's true and false and this one is false. So what am I going to do now that I have a third letter? I'm going to do the exact same thing again. I'm going to assume the cases where, with two letters, this is it, but then this one's true all the time. And then I'm going to do the same things again. True, true, false, false. True, false. True, false. But then now this time when these ones are all false. Right? And that should take care of all the cases. So yeah, having three independent statements of each other now results in 8 different cases. Okay. No big deal. No big deal. I'm not scared. Let's look at it, right? So what statements do we need? We need the statement P or Q. And then once we have that statement, we're going to look at the statement P or Q implies R. Okay. That should take care of the left side, right? What about the right side? On the right side, I need the statement P implies R. I need the statement Q implies R. And then I'm going to look at the statement of their I don't want to say intersection, but I'm going to just put an and in between them, right? Alright, so let's see. Well, okay, I mean, again, remember what are the rules for OR? For OR, only at least one of them has to be true, right? So only at least one of them has to be true, so this one's true. At least one T, this one's true. At least one T, at least one T, at least one T, at least one T, at least one T. And over here is the only one where that's false. Okay. So then now we're looking at if this, then that. So true, true makes it true. True, false makes it false. True, true makes it true. True, false makes it false. True, true makes it true. True, false makes it false. Yeah. True, true makes it true. But then false, false makes it true. Hopefully I didn't do anything wrong, but I think it looks good. Okay, now we're looking at the statement if P then R. So if P then R. So true, true makes it true. True, false makes it false. True, true makes it true. And then true, false makes it right. So true, 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 false. True, 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 false. And over here, they all start with false, right? So then these are all going to be say true, 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 true. Okay, now the statement Q and R. So these two, this time they're like next to each other, right? So true, true makes it true. True, false makes it false. And then false, false on the next one. So true, true here. And then true, true makes it true. True, false makes it false. True, true. I'm kind of shaken up. Let's see if it actually works out. So then now we're looking at the intersection, or we're just looking at the and statement between these two, right? So this and that. So if this is true and this is true, this is true. If this is false, this is false, this is false. This is true. True. I think I already did something wrong, huh? True. Yeah, they don't match up, right? So true. Okay, so these two are the ones that should be matching up. True, true, false. True, false. So the only place where they don't seem to match is like right here, right? So I'm just gonna write this. Why did not match? So did I do this one right? P then R. P is true. P is true, but R is false. So then this is false. Okay, so now they match, right? Because if this one's false, I got this one fine, right? If this is false, it's false, it's true. But because we're looking at and over here, right? If this is false and that's true, then this needs to be false. So now this row, I mean this column, true, false, true, false, true, false, true, false, true, false, true, false. Yeah, now these two columns do match. So again, the if and only if statement will be a tautology. Oof. Damn, I almost messed that up. I mean, I guess I did, right? But I caught my mistake. That's why when you take a test, you need to make sure you double check your work, right? Or I don't know, maybe I did another mistake. Call me out. Leave that in the comments, right? So yeah, these are basically the major ways of proving stuff, you know. So direct proof, proof by counterexample when you want to disprove somebody. Proof by contradiction, you'll see this a lot. Proof by contrapositive and proof by cases. Well, again, I don't want this to be a gigantic video, so I'm gonna leave it right there. Let me know what you think. Like and subscribe. See you later.